Thanks. Good morning. I guess it was probably about 3 years ago I was wandering around the Academy exhibit hall, and John Allman was there with these black plates and x-rays showing this radiolucent implant. And I thought that was really interesting and hadn't really thought about what its properties were, but just that it was interesting in terms of the ability to visualize the fracture site. By way of disclosure, I do serve as a consultant for Invibio. So in the very beginning, we had open reduction and internal fixation. And this was associated with lots of periosteal stripping, and fracture healing was very slow because of that. We had absolute stability in which each fracture fragment was perfectly reduced and rigidly fixed with a lag screw whenever possible. And fractures healed very slowly by these osteonal cutting combs and primary bone healing. Implants during this area of fixation had to be strong. They had to be thick in order to last long enough for the fractures to heal. But we also know that fractures can heal in a different method, secondary bone healing with callus when you have motion at the fracture site. And we began to develop minimally invasive methods in which we minimized the periosteal stripping, minimized the soft tissue further assault at the fracture site in order to promote union. And in this case, we fixed things with relative stability, and we expected callus. Well, the problem became that some of our current metal plates, specifically in the distal femur, may actually be a little too stiff. And these stiff plates worked well when we were doing direct reduction, but not quite so well for a minimally invasive technique with desires to have relative stability. In this retrospective review of distal femur fractures fixed with the locked plate, they found a 20% non-union rate. And the non-unions, when they looked at them, had limited callus, suggesting that the mechanical factors might play a role in terms of that fracture healing problem. In another retrospective review of 283 distal femur fractures, independent risk factors for non-union you see here, and the bottom one was the use of a stainless steel plate compared to titanium, and we know they have different moduluses of elasticity. We know that there's an increase in distal femur fractures, specifically with respect to periprosthetic fractures, as we have more and more total knees being done. And metal implants have limitations, and they may limit our ability to achieve better outcomes for these patients. Their fatigue life is sometimes shorter than the healing time, and there is an inability to tailor the stiffness of the implant itself. Certainly we can change the working length, we can choose different fracture fixation constructs, but the metal itself is a given in terms of its stiffness. And numerous basic science studies have shown us that the more flexible fixation is beneficial in terms of achieving callus healing. And companies have tried to develop different ways in order to provide improved motion at the fracture site. So Zimmer came out with their motion lock screws and the concept of far cortical locking. Synthes for a period of time had a dynamic locking screw where you had more motion at the fracture site with this screw. More recently, Zimmer has been developing this active plate in which there is a silicone insert that provides some degree of flexibility within the screw hole construct to achieve more motion at the fracture site. If we go back into the literature in the 1980s, carbon fiber reinforced plates were first being studied. And this was done with epoxy resin rather than with PEEK. The benefits or the differences was that the Young's modulus was about a third that of stainless steel plates, and they exceeded the yield strength of the stainless steel plates. And so they used these multi-laminated carbon fibers and then epoxy rather than PEEK. And they reported first on a preclinical study. This was a transverse mid-tibial sheet model fixed with a plate. All of these fractures healed with abundant callus, and normal strength was achieved comparable to the contralateral side at 20 weeks. They also did another one in which they had a double osteotomy, so they removed a centimeter of bone, so it was devascularized. And again, all of these went on to heal, normal strength to the contralateral side achieved by 25 weeks. And they also reported then on an early clinical study, 20 patients, average age 21 years, with a transverse short oblique or mid-shaft tibia fracture, and they excluded open fractures, so all closed fractures. 19 of 20 of these achieved union. They had one hypertrophic non-union early in the series, and they had modified the plate because they felt that their initial plate was not stiff enough, and that led to the hypertrophic non-union. They had 3 deep infections, but reported that even despite the infection, that the fractures went on to unite. And here is an example showing one of these clinical cases that's in the literature, showing the abundant callus at the fracture site. And they concluded that the desirability of motion at the fracture site was clearly shown, that external bridging callus appeared in all of the cases, but it was in varying quantities, and it produced a fairly rapidly sound union. And that they went on to say that the accurate juxtaposition of the fragments is clearly not essential, since external bridging callus has a most forgiving nature in bridges small defects. They also studied this in 19 other cases, which they categorized as problem cases. They're complicated either by infection, non-union, or comminution. These were in a variety of locations, and 18 of 19 of these went on to heal and have satisfactory clinical results. Well, why didn't this catch on from the 1980s until just a few years ago? Well, it was even economics were driving things then. They had a higher cost relative to metal implants. At that point in time, our reliance was really on direct reduction, which often requires contouring of the plate. And at that time, there wasn't locking screw technology. And so it didn't permit indirect reduction of a non-contoured plate. So there were some challenges. There's also a concern over this higher than average infection rate that was reported in this early clinical series. Well, in the 1990s, manufacturers changed many of them to titanium for its better match to modulus of elasticity of bone. Discussed this biologic fixation with titanium. It was also more expensive, and there were problems of cold welding when we tried to remove these implants. And by the late 1990s, PEEK had emerged as the leading high-performance thermoplastic candidate to replace metal. And PEEK is polyether ether ketone, originally developed in the late 1970s for the aerospace industry, and Invibio began commercially marketing this in April of 1998. And PEEK spinal cages have been used by our spine colleagues since 1999, so almost 2 decades now. Carbofix is an Israeli company that I first saw at the academy several years ago. They manufacture carbon fiber reinforced PEEK implants, IM nails, and plates. And since they started, several other companies are also offering various PEEK-related implants. Here's an X-ray of their intramedullary nail in the humerus, a distal radius fracture, proximal humerus, distal femur. And the advantage of these carbon fiber implants is you have a lower modulus of elasticity, so you're going to have more motion at the fracture site, hopefully more callus formation. Another advantage is it's radiolucent, so you can see the fracture, potentially allowing you to improve your reduction because you're not being obscured by the shadow of the metal plate. You can see healing in all 4 planes in your postoperative follow-up x-rays. You can obtain a CT scan or an MRI. You can also provide radiation therapy, so some of our oncology colleagues prefer that. It has superior fatigue life to metal implants. In my first case, I chose an easy one. This was a 28-year-old motorcycle accident, had this open proximal humerus fracture. DeVere came out for the case. And here's his CT scan and his intraoperative fluoroscopy. Admittedly, still in a little bit of varus despite efforts to improve things. Radiographs at 2 months, seeing some callus formation at 4 months. At 7 months, and at this point in time was really unclear whether or not the shaft had fully united to the head, and so got a CT scan which did show continuity of the healing bone. And here's a 1-year follow-up x-ray and his 1-year range of motion. Second case, I chose a little easier one, simple 2-part fracture. Easy to see the reduction, can get a very accurate intraoperative imaging. Here's his 3-month post-op follow-up x-ray and his range of motion at that time. So one of the questions that I had is the locking screw construct in these plates. How does it compare to, say, a stainless steel plate? And so we did a study to compare the mechanical stability in carbon fiber reinforced PEEK plates with those in stainless steel plates. We examined the impact of screw reinsertion in the PEEK plates. And we also examined the impact of off-axis screw insertion. We compared Carbofix plates with stainless steel Synthes proximal humerus plates. And all the screws were tightened to the manufacturer's recommendation of 1.5 Newton meters. They were fixed to a Instron servohydraulic test machine, and a perpendicular force was applied to the screw. We measured stiffness and load to failure, which was defined as collapse of the screw plate interface or pull-out or 2 millimeters of screw displacement. And we studied 3 different conditions: the stainless steel plate with the on-axis trajectory, with a screw after being removed and then reinserted on an on-axis trajectory, and then the insertion of a screw that was 10 degrees off the axis. And we used a custom jig in order to put that screw in on that 10-degree off axis. And we inserted screws both into the proximal aspect of the plate and into the shaft portion and analyzed those independently. A t-test was used to compare the means, and the results was that the load to failure in the diaphyseal locking screws was significantly greater in the CFR PEEK plates compared to stainless steel, and the values are shown here. There was no significant difference in the stiffness or load of the proximal screws, so equivalent. And stiffness and load did not vary significantly with this screw reinsertion. The distal locking screw stiffness and load to failure in the diaphyseal holes was significantly better when it was inserted on axis compared to the 10-degree off axis, which is what we've seen in other plating systems. So we concluded that the locking plate CFR PEEK were comparable or superior in terms of the engagement of the locking screw compared to traditional stainless steel plates, and didn't seem to be particularly detrimentally impacted by reinserting a screw into the same hole a second time. And again, off-axis screws, just like in other systems, are not going to be as mechanically stable as on-axis screws. So in summary, carbon fiber reinforced PEEK permits relative stability with callus formation at the fracture site, has greater fatigue life than metal implants, has the benefit of radiolucency, which can help both intraoperatively and postoperatively in terms of your assessment of the fracture healing and reduction. It's been successfully used by our spine colleagues for 18 years and may actually offer improvements in terms of our care of patients and maybe a paradigm shift in terms of how we go about fixing fractures. Thank you.